Hello, this is Rupesh Reddy from Government Engineering College, Hassan. This is the video of second section of the fifth module, Digital Signal Processor, prescribed for fifth semester Electronics and Communication Engineering students. Here, we will be discussing about digital signal processor hardware units. Specifically, we will be discussing about multiplier and accumulator unit, shifters unit, address generators, and then at the end of this particular session, we will be discussing about fixed point formats. So to begin with, the digital signal processor hardware units. So a multiplier and accumulator unit, shifters, and address generators. All these are the special building blocks available in our digital signal processor architecture, which are not available in general purpose microprocessor. So if we consider multiplier and accumulator unit as compared with the general purpose microprocessor, which is based on von Neumann architecture, the digital signal processor uses multiplier and accumulator unit, which is a special hardware unit which enhance the speed of digital filtering. This is a dedicated hardware and the corresponding instruction is generally referred to as MAC operation. You can see the basic structure of a MAC unit here. You can observe here, this particular MAC unit has a multiplier with pair of input registers here, each holding 16-bit input to this particular multiplier. The result of this multiplication is accumulated in a 32-bit accumulator here. This particular result register holds the double precision data from the accumulator. So this is a multiplier and accumulator unit which performs multiplication and accumulation. So what's the function of this MAC unit is, if you compare this particular unit with our general purpose microprocessor, if you want to perform a single multiplication and accumulation unit in our general microprocessor, what we have to do is we have to write a program to accept the number of inputs for which we need to have sum of product kind of operation. Suppose there are 5 numbers are there. If we want to perform sum of product of those 5 inputs, then we have to have 5 times of accumulation of those 5 inputs. But so what we have to do there is we have to write a program such that every time we have to fetch the data or fetch 2 operands, that is multiplier as well as multiplicand. We have to multiply and we have to store that multiplied output somewhere. To that we have to take input and multiply, and we have to add that with the stored value. So it takes lots of instruction to perform that. Obviously, our general purpose microprocessor takes more time to perform such particular multiply and accumulation kind of operation. If we consider this MAC unit which is available in our digital signal processor, see, once these 2 operands, that is multiplier as well as multiplicands are made available to this X register as well as Y register, see, within a single cycle, we can expect the multiplied output here, accumulator. Okay, whatever the result, previous result, which is here presented in the accumulator, gets added with the present product, which we obtain here. Okay, hence this multiplier and accumulator unit makes our MAC operation or sum of product kind of operation which is faster, because most of our digital signal processor or signal processing involves this kind of operation, filtering kind of operation. Again, filtering is nothing but the convolution of the incoming signal with the linear time invariant systems unit impulse response. So output will be filtered output. That filtered output we can consider as the convolved output, or we can say that as a MAC operation. So this is about the MAC unit. If we come for shifters, so in digital filtering, to prevent overflow, what we have to do? We have to scale. So a scaling operation is required. Okay, a simple scaling down operation shifts data to the right. Okay, a scaling up operation shifts data to the left. Shifting data to the right is same as dividing the data by 2 and the truncating the fractional part. So shifting data to the left is equivalent to multiplying the data by 2. If we consider example for this, if we consider a 3-bit data which is representing the value 3 in decimal, so we can binary we can represent it as 0, 1, 1. Okay, so now if we want to shift this 0, 1, 1 to right, what happens? So this 1 comes here, 0 will comes here, and the LSB occupied with 0. So 3 becomes, once it shifts to the right, the value becomes 1. That is 3 by 2. Okay, so this is 1.5. So if we truncate, the result will be 1. Okay, see, if we consider the same number 3 again, and if we shift this value to the left, what happens? This one comes here, this one comes here. Okay, so and LSB will be occupied with a 0. So value of this particular thing is 6. So that is, this will be 3 into 2, that is 6. That means shifting right will be dividing by 2 and shifting to the left indicates multiplying by 2. So which represents scaling. So here it is, we can call it as scaling up, and this is as scaling down. So this scaling up and scaling down can be done using the shifters which are available. These are the dedicated hardware which are available in the digital signal processor architecture. One more dedicated hardware or dedicated block which is present in our digital signal processor is address generator. The digital signal processor generates the addresses for each data on the data buffer to be processed. A special hardware unit for circular buffering is used. Okay. In this figure, you can observe here. See, this is the basic mechanism of circular buffering of a buffer having 8 samples. You can observe here 8 data samples, x of n, x of n minus 1, x of n minus 2, x of n minus 3, x of n minus 4, x of n minus 5, x of n minus 6, and x of n minus 7. So there are 8 data samples. So in circular buffering, a pointer is used and always points to the newest data sample. You can observe here. After the next sample is obtained from analog to digital conversion, the data will be placed at this particular location, that is x of n minus 7 for the current sample. So the original location for x of n becomes the location for the past sample x of n minus 1. The process will going to continue according to the mechanism as we considered before. Okay, for each new data sample, only one location on the circular buffer needs to be updated. So the circular buffer acts like first in, first out buffer. Hope you are getting this. But observe, each data or datum on the buffer does not have to be moved. You can observe here. So this is the simple illustration of 2-bit circular buffer. Okay. Here you can see there is data flow to the ADC, analog to digital conversion. Okay. A, B, C, D, E, and F here. And a circular buffer, initially, it is containing these 4 values, A, B, C, and D. Okay. The pointer specifies the current data of D. Okay. The equivalent first in, first out buffer is, observe, you can hear pointer. The current data of D at the top of the memory here. When E comes, when this particular E comes in, observe here, this shifts, data gets shifts here. Okay. When this E comes, see, in middle drawing here, the circular buffer will change the pointer. Pointer will be changed to the next position and update the old A. Okay, you can observe here, A is get updated with the new datum E. You can observe here. Though these are get shifted to down here, BCD gets here, BCD, but A goes first in, first out, A goes back. But this location where D was there, that will be occupied by E. But the pointer where here it was before, now pointing to the new datum E. This E gets the location of A, which was present earlier. So it casts the pointer only one moment to update one datum in one step. However, on this right side, the first in, first out has to move each of other data down to let in new datum E at the top. Okay. For this first in, first out, it takes 4 data movements. Okay. So in the bottom line, you can observe here the incoming datum F for both the circular buffer and the first in, first out buffer continues to confirm the same observations. Okay. So like finite impulse response filtering, the data buffer size can reach several hundreds. Hence, using the circular buffer will significantly enhance the processing speed. And if we consider, next let us consider the comparison on fixed point formats as well as floating point formats. Okay, in order to process the real world, we have to select an appropriate digital signal processor as well as a digital signal processing algorithm, or algorithms for certain application, we can say. Whether a digital signal processor uses a fixed point format or a floating point method depends on how this processor's central processing unit performs arithmetic. Okay. A fixed point digital signal processor represents data in 2's complement integer format, and this manipulates data using integer arithmetic. But if we come to this floating point format, a floating point processor represents numbers using mantissa, that is fractional part, and exponent in addition to the integer format. Okay, and this operates data using floating point arithmetic, but our fixed point format operates on integer format. As the fixed point digital signal process operates using integer format, which represents only a very narrow dynamic range of the integer number, a problem like overflow of data manipulation may be possible. Hence, what we have to do is we need to spend much more coding effort to deal with such situations. We may use floating point digital signal process, which offers a wider dynamic range of data so that coding becomes much easier. However, the floating point digital signal processor contains more hardware units to handle the integer arithmetic. The floating point arithmetic, hence, is more expensive and slower than the fixed point processors in terms of instruction cycles. It is usually a choice for prototyping or proof of concept development. When it is time to make the DSP an application specific IC, a chip designed for a particular application, a dedicated hand-coded fixed point implementation can be the best choice in terms of performance and small silica area. The format used by DSP implementation it may be a fixed point or floating point. So with this, we're going to conclude this particular session. Thank you.